Example 4.27. A line charge with a linear charge density lambda prime is placed parallel to, and a distance r away from, the axis of a conducting cylinder of radius b held at a fixed voltage such that the potential vanishes at infinity. Find a. the magnitude and position of the image charges. b. the potential at any point expressed in polar coordinates, where the line from the center axis to the line charge is the positive x-axis direction.
C. the induced surface charge density. D. the force on the charge. Solution: to solve using the method of images, we want to place an image linear charge density lambda double prime equals alpha lambda parallel to the lambda prime linear charge density at position inside the cylinder in the positive x-axis direct line formed by the perpendicular to the cylinder axis, origin, and to the outside linear charge axis. We know the potential due to a linear charge density goes as radial distance from the line charge. In the relevant 2D polar coordinates, theta, rho, for line charge at rho prime and observer at position rho we have potential, see the equation. And for the mirror line charge will be at position rho double prime with charge density lambda double prime equals alpha lambda, see the equation shown. The total potential in the cylinder exterior is thus, see the equation. For phi of rho to remain finite at infinity, not to mention 0, we must have alpha equals -1.
See the equation shown. So, we've obtained the magnitude of the line charge. Now let's determine the position of the line charge. This is done by satisfying the zero potential at the conducting surface constraint. Phi of rho equals b equals 0. When the absolute value of rho equals b, we can write the absolute value of rho minus rho prime equals beta times the absolute value of rho minus rho double prime. Writing in terms of the magnitudes along the x-axis, we have 2 points where x-axis intercepts the cylinder, providing 2 relations. See the equation. These can be grouped to give rho double prime equals b squared over rho prime for the position of the line charge and to solve for beta. See the equation shown.
B. Thus, at the cylinder surface, we have, see the equation. The potential at any point is thus, see the equation shown. Comparing with earlier derivations we have agreement, see the equation. C. For the induced surface charge density we have, see the equation shown.
See the equation. See the equation shown. See the equation. See the equation shown.
See the equation. See the equation shown. D. See the equation. Example 4.28. Suppose you are told the potential on the surface of a cylinder and asked to do a series solution. Solution by series solution, see the equation shown. Since the origin is included in the region of consideration, all the b sub n are 0. And using
see the equation. See the equation shown. And since via orthogonality see the equation. So see the equation shown.
See the equation. Thus, see the equation shown. When rho is greater than b, the potential changes sign. Now let's solve 2.8 via Green's functions, see the equation. With conditions, 1, 0 is less than r prime is less than b, 2, phi sub 0 equals con st, 3, tau equals negative tau prime, 4, r prime over b equals b over r, and v, rho prime divided by rho equals r divided by b. So, phi sub c equals 2 tau ln of r over b, for a grounded surface. Thus, phi equals 2 tau ln of rho prime r over rho b, and g of x comma x prime is then g equals 2 ln of rho prime r over rho b. For the problem at hand, let phi sub 0 prime equals 2 tau ln k at the surface. Then, see the equation shown. And
see the equation. Since we have rho of x equals 0 and Dirichlet boundary conditions. See the equation shown. Thus, see the equation. And see the equation shown. The results are the same. Example 4.29. A long hollow cylinder is split lengthwise by a gap. The halves are maintained at different potentials. V sub 1 and V sub 2. The cylinder radius is b. A. Show the potential inside.
B. Calculate the surface charge densities. Solution using series solution or Poisson's integral equally messy, but at the integrals are straightforward, so let's use that, see the equation. So, see the equation shown. See the equation. Using see the equation shown.
See the equation. So, the 1st integral becomes see the equation shown. See the equation. See the equation shown. Etc. b. We have
see the equation. And see the equation shown. Example 4.30. A long hollow cylinder is split lengthwise into quarters by gaps. The quarters are maintained at alternating potentials, positive V and negative V. With the cylinder radius equal to b solution, we have gradient squared phi equals 0 inside the cylinder, e.g., Laplace's equation in cylindrical coordinates with cylindrical symmetry reducing to polar coordinates in 2D, with no charge inside. For polar coordinates, ds squared equals d rho squared plus rho squared d phi squared goes to the absolute value of g equals rho squared, and g sub rho equals 1 comma rho sub phi equals rho squared goes to the phi th power of g equals 1 over rho squared comma a and d times th of e times rest times c ro period. Thus, see the equation. With phi of rho comma phi equals r of rho psi of phi leads to
see the equation shown. See the equation. Note that psi equals a e raised to the iv phi power indicates that v is integer valued, otherwise psi is not single valued, and e raised to the iv of 2 pi power equals 1. Thus, have the solutions. See the equation shown. And, for v equals 0 solution, see the equation. So,
see the equation shown. The region under consideration for the problem includes the origin, so solutions, finite, require b right single quotation mark s equals 0, see the equation. A sub m times b raised to the absolute value of m power equals 1 over 2 pi the integral from 0 to 2 pi of phi of b comma phi prime, e raised to the exponent negative I'm phi prime and exponent d phi prime 1 over 2 pi the integral from 0 to 2 pi of phi of b comma phi prime, e raised to the exponent negative I'm phi prime and exponent d phi prime. See the equation shown. Thus, see the equation.
See the equation shown. Now let's get the a sub m. See the equation. See the equation shown. See the equation.
See the equation shown. See the equation. See the equation shown. See the equation. And we have
see the equation shown. So, 0 for m odd and plus or minus 1 for m even. Similarly, e raised to the negative m pi over 2 power minus 1. Tilde 0 f of or times m equals 4n times or times m equals 2 times 2n plus 1. Over bar, and this is negative 2 for m equals 2 times 2n plus 1. Thus see the equation. See the equation shown. And otherwise for m equals 2 times 2n plus 1, a sub m equals positive 4v over m pi b raised to the absolute value of m power equals 0. Thus, we can answer with the following.
A phi of rho comma phi equals the sum from m equals negative infinity to infinity of 4v over m pi b raised to the absolute value of m power times rho raised to the absolute value of m power e raised to the m phi power f of or times m equals 2 times 2n plus 1, e.g., m equals 2, 6, 10. See the equation. See the equation shown.
B. Some series. See the equation. See the equation shown. See the equation. See the equation shown.
See the equation. See the equation shown. See the equation. Example 4.31. Obtain the two-dimensional Dirichlet Green's function for the exterior of a cylinder of radius b. Solution standard 3D Green's formula for Dirichlet cases. See the equation shown. To calculate the capacitance, let one of the cylinders have phi equals 0 and put charge q on the other. Thus, phi equals 0 times on times a sub 1 right double arrow no surface term. Assume unformed line charge density on a slice lambda over 2 pi a sub 2 dot then.
See the equation. Using Jackson's 2ND form, see the equation shown. And setting rho equals d almost equals rho prime comma d is much greater than a sub 1 comma a sub 2 comma simplifies to see the equation. Thus, see the equation shown. Thus, C equals Q divided by L over V equals lambda over V asymptotically equals 1 over 4 ln of D over A. Same as 1.7.
C if rho is inside, rho prime and rho double prime are swapped and tau prime swapped. This introduces two negative signs, so the same formula works both interior and exterior. Example 4.32. A. Use example 4.31 and obtain the Poisson-integral form of the Dirichlet problem in a circle. B. Obtain the solution using Cauchy's theorem instead. A. Exactly like example 4.28, example 4.31, radius B. See the equation. See the equation shown. Thus, see the equation. See the equation shown.
B. Use Cauchy's theorem to derive the Poisson-integral solution. Cauchy's theorem. See the equation. For z inside are, note, f of z equals 0 for z outside curve. See the equation shown. See the equation. See the equation shown. We then take real part to get Poisson's integral. Shift origin to take advantage of symmetry now have.
See the equation. A. BC's are now parity even cos and cosh functions. See the equation shown. Where n, m are odd numbers. See the equation. We know see the equation shown. So,
see the equation. See the equation shown. Equals 16v over pi squared n prime m prime, the hyperbolic cosine of pi over 2 the square root of n prime squared plus m prime squared, negative 1, raised to the exponent n prime minus 1 over 2 end exponent times negative 1, raised to the exponent m prime minus 1 over 2 end exponent. See the equation. B. See the equation shown.
See the equation. C. See the equation shown.